the last thing we're going to look at with complex numbers is this thing called roots of unity. So basically, solutions to equations of this form. Z to the power of n is plus or minus 1. Majority of the time it's positive 1, but occasionally you do see negative 1, and that has its own little intricacies. So that's what's known as the nth roots of unity. Now, if we were to draw it on our argand diagram, we know all the solutions would sit on the unit circle because the modulus would equal 1, and it would form an n-sided polygon because of that symmetry I was talking about. So they're going to be nicely regularly spaced around that circle, and if we were to join them up, we get a neat polygon. So let's have a look at z to the power of 5 is equal to 1. Now, if we use our idea that we saw before with roots, we know, well, that's going to be 2 pi k, going to be plus 0, because the argument of 1 is just 0. So really, it's just 2 pi k on 5. And I'm using the conjugate idea, which I can do, because all the coefficients, well, there's only one number, it's 1, and it's real. So I know they're going to appear in conjugate pairs. So I'm going to go 0, I need 5, so I'll go plus or minus 1, plus or minus 2, and that'll create the conjugates straight away. And so there they are. Cis 0, which is the solution we would have expected. Cis 0 is 1, and we know 1 to the power of 5 is 1. So we're expecting that one. But then the others, cis 2 pi and 5, cis minus 2 pi and 5, 4 pi and 5, minus 4 pi and 5. Now, if I'd done that geometrically, remember I said, once we know the first solution, we know all the solutions because of the symmetry. So the first solution was the obvious one, cis 0. But if there's 5 solutions going around the unit circle, then they must be separated by 2 pi and 5, which is 72 degrees, isn't it? So 72 degrees later, there must be cis 2 pi and 5. Its conjugate must also be there. So cis minus 2 pi and 5. Go around another 72 degrees. There's cis 4 pi and 5. Its conjugate must be there. Cis minus 4 pi and 5. So as I say, they all sit on the unit circle, and if we join them up, we'd get a pentagon in this case, a 5-sided polygon. Okay. So continuing playing with the roots of unity, we get some interesting questions. So omega is a complex root. Now, the big mistake people make here is to assume they're talking about cis 2 pi and 5. But it could be any of the complex ones. Now, sometimes they'll say, let omega be cis 2 pi and 5. So they'll say, okay, let it be that first one. But that's not what our question says. Our question simply says, it's a complex root. It could be any of them. So we then have to show that it's squared, cubed, 4, and to the power of 5 are the other solutions. Now, if they had told us the first one, I'll just zoom back again. If they had told us omega was specifically cis 2 pi and 5, well, then that would be quite easy. I could just use de Mail's theorem and say, oh, well, omega squared would be cis 4 pi and 5. Oh, yes, that's one of the other ones. Then cubed would be 6 pi and 5, which is the same as minus 4 pi and 5, and so on and so on. But again, that's not what our question says. So we can be a little bit tricky here. So we know there are going to be solutions to z to the power of 5 is equal to 1. And we told omega is a solution. So therefore, when I substitute it in, I must get the answer 1, because it's the solution to the equation. Now, if omega to the power of 5 is 1, then omega to the power of 5 to the power of 5 would be 1 to the power of 5, which is also 1. So omega to the power of 5 is also a solution. The other thing I know is omega squared to the power of 5 is the same as omega 5 squared, just playing with the index laws there. But we know omega to the power of 5 is 1, and 1 squared is 1. So hang on a sec. When I substitute in omega squared, I get the answer 1. It must be a solution. I can do the same with the cube. Omega cubed to the power of 5 is the same as omega to the power of 5 cubed. But I know omega to the power of 5, that's 1. And 1 cubed is 1. So when I substitute in omega cubed, I get the answer 1. It must be a solution. And exactly the same, playing with the indices there, I can show that that's also 1. So it must be a solution as well. So I haven't actually specified which one omega is. But what I have shown is, if I know it is a solution, I can generate all the other solutions playing with the powers. So yep, if omega is a root, then so will omega squared, cube, power of 4, power of 5 be. In fact, omega to the power of 5, that is a specific solution. That'll always be 1. We now have to prove that 1 plus omega squared, they all add up to be 0. Several ways we can do this. Here's the first way. Remember, it's a solution to an equation. So I could say the sum of the roots, and we just said these are all the roots, omega, omega squared, omega cubed, would equal minus b on a. Now our equation is z to the power of 5 minus 1 equals 0, if we write it as a polynomial equals 0. B in that case, it would be the coefficient of the power of 4. There isn't one. So that is just going to be 0. And omega to the power of 5, well, we know that one's equal to 1. So there we have our result. 1 plus omega squared, and so on. Now, they'll often ask you to prove this, but if they don't, it is okay in a roots of unity question to sort of say, well, as omega cubed, if we were doing cube roots of unity, as omega cubed is equal to 1, then we know 1 plus omega squared is equal to 0. As I say, a lot of times they'll ask you to prove it, but if they don't, we can just use the idea. Another way of doing it. Well, there's the equation again, omega to the power of 5 minus 1. But I can factorise that. Factorise to be omega minus 1, and then the powers of omega go down by 1. Powers of 1 go up by 1. Now, if I was to solve this equation, I get two possibilities. I get the possibility in this first parenthesis that omega equals 1. But we know that's not true, because we specified omega was a complex solution. So it can't be equal to 1. Therefore, the other parentheses must equal 0, and that's what we're trying to prove. So remember that idea for this question. We can always factorise to the power of n is start with omega minus 1, and then it's just 1 plus omega squared all the way up to n minus 1. All right, that's one way. Another way we could do it. There's yet another way. Oop. What I've got there is a geometric series. 1 plus omega squared, omega cubed, and so on. So if I use my geometric series formula, then I've got a is 1, r is omega, number of terms is 5. So a, r to the n minus 1 over r minus 1. Okay, we've got omega to the power of 5 minus 1. But hang on, omega to the power of 5, we know that's equal to 1. So that's going to equal 0. So there's a third way we can prove that. Which way do I tend to go? I tend to go with the sum of roots one. I think that's quickest. Just saying, sum of the roots is equal to 0. But it really doesn't matter. I mean, they're all pretty quick. We're going to find a new equation. It's going to be a quadratic. We know the solutions, or the roots to this equation. One will be omega plus omega to the power of 4. The other will be omega squared plus omega cubed. Sum of the roots of this new equation will be omega plus omega to the power of 4 plus omega squared plus omega cubed. But we now know the 1 plus omega squared plus omega cubed plus omega to the power of 4 is equal to 1. Therefore, omega plus omega to the power of 4 plus omega squared plus omega cubed is negative 1. Okay? We just proved they all add to be 0. I just want the omega to the omega 4, move the 1 to the other side, they've got to be negative 1. Okay, so I know the sum of the roots of this new equation is negative 1. Product of the roots. Well, if I expand that all out, omega cubed, omega power of 4, omega power of 6, and 7. But we know omega to the power of 5 is equal to 1. So I can rewrite that. Because if omega to the power of 5 is 1, then omega to the power of 6 is the same as omega. And omega to the power of 7 is the same as omega squared. And look what we've got left with again. The same sum, which we know is negative 1. So the product of the roots is also negative 1. So our quadratic will be x squared minus the sum of the roots. So minus 1, positive 1x, plus the product of the roots, negative 1. There's our equation. Going to play with the cube roots of unity. This time they're telling us, so we don't have to derive it. They're telling us, okay, it's fair enough to assume 1 plus omega squared is going to equal 0 for the cube roots of unity. We want to work out what 1 plus omega squared all to the power of 3 is. Now you could expand the whole thing out, but there's a quicker way. I've got 2 terms there. I can always, using 1 plus omega squared equals 0, turn 2 terms into 1 term by simply moving the other term to the other side. And I should be able to get an expression. I've got 1 plus omega squared. So in this case, if I move omega to the other side, I'll get 1 plus omega squared is negative omega. That's easier to work out now, because negative omega cubed is negative omega cubed. We're playing with the cube roots of unity. Omega cubed is 1. So we get negative 1 as our answer. These fractions. Okay, algebraic fractions, but again, here I've got a denominator with 2 terms, but I can turn those 2 terms into 1 term. So 1 plus omega, I'll move the squared over this time. So I'll get minus 1 on omega squared, and then the 1 plus omega squared, move the omega over. I get minus 1 on omega. That's an easier fraction to deal with. So playing with that fraction, minus 1 minus omega over omega squared. But hang on, minus 1 minus omega, that's 2 terms. I can turn that into 1 term. In this case, it's the negative, but I'd move the omega squared to the other side. I'll get omega squared on omega squared, which is 1. Now, you might be thinking the answer is always going to be 1 and minus 1. And so if you're struggling and you go, oh, what's the answer? 1. Minus 1, 50-50 chance. I think they're going to be looking for working out. Okay, we're going to create a cubic equation. The 3 roots this time, 1 plus omega squared. Well, I know z minus 1's a factor. That one's easy. I'm going to create a quadratic with these 2 roots. Again, we could always say minus the sum of the roots plus the product of the roots. And I could actually have done this quicker. I'll come back to that. Okay, 2 plus omega squared. Well, 1 plus omega squared is 0. So therefore, I've got 1 plus omega squared. 1 plus 0. So that's just 1z. And over here on the other one, well, 1 plus omega squared is 0. Leaving me with omega cubed. Omega cubed is equal to 1. There we are, it's factorised. Now, we want the actual equation. I suppose that is an equation, but let's expand it out to make it look like, I guess, what we were expecting. Z cubed minus Z squared plus Z. Oh, there's another minus Z squared. Oh, there's another Z. There we go. I was saying there would have been a quicker way. Because remember, 1 plus omega, that's 2 terms. I could have turned that root into minus omega squared. And the 1 plus omega squared, I could have turned into the root minus omega. And so it would have created different ones, but they would have come up with the same answer eventually. So I want to actually solve this. And it's looking like, hang on, roots of unity, because we're starting to see that pattern. So how do I do it? Well, that's tough to solve. So I'm not going to solve that equation. Because I know z to the power of 6 minus 1 would be z minus 1 times that. And z to the power of 6 minus 1 equals 0. That's a much easier equation to solve. It's the 6 roots of unity. So I'm going to change it. Because, as I say, I know the solutions to z to the power of 6 would be 2 pi k on 6. I need 6 solutions, so I get 0, plus or minus 1, plus or minus 2. 3 will make up the 6th solution. So, all right, back to this equation. I'm going to turn it into z to the power of 6 minus 1. How do I do it? I just multiply top and bottom by z minus 1. So what that's now telling me is, with z to the power of 6 minus 1, that's actually the top of this equation. That's what I'm solving. However, I only need 5 solutions, because I'm solving to the power of 5. Well, I know 1 is not a solution to this equation, for a couple of reasons. if I sub it into the equation, clearly I'm not going to get 0. But the other reason, I created the solution when I multiplied top and bottom by z minus 1. The original equation, it's not part of that. So therefore, it must be all of these solutions up here, the cis 2 pi k on 6, but not including the solution z equals 1. It's all the others. So if we write all the others down, we'll get cis pi on 3, its conjugate, 2 pi on 3, its conjugate, and pi. Nice numbers, we could actually work all those out. Did I? Yes, I did. Half plus root 3 on 2i, and so on and so on. So if you see that standard pattern, okay, it's a rare equation, it's a specific type, but we can use roots of unity to solve that. Quite an old question now, 20 years ago. So this time they're telling us which particular root omega is. It's the first one, it's the 2 pi on 9 plus I sine 2 pi on 9. But it's another way of saying it, show that all the powers are a solution. Well, that's simply, rather than say, show that omega squared, cubed, 4, 5, 6, 7, 8, 9, they've simply said omega to the power of k, where k is an integer. That would always be solutions. Okay, well, z to the power of 9 is equal to 1. So I get 2 pi k on 9. Now, in this case, I'm not going to go plus or minus. I suppose I could have. But anyway, 0, 1, 2, 3, 4, 5, 6, 7, 8 will create all those powers. But hang on, 2 pi k on 9. I could rewrite that. Using Dewey's theorem in reverse, I could say, well, that's the same as saying cis 2 pi on 9 all to the power of k. Because Dewey's theorem would say, bring the k in and multiply the argument. Well, cis 2 pi on 9, that's what they told me omega is. So that's equal to omega to the power of k. And k is an integer. So now that we know that, we're going to prove omega plus omega squared plus omega cubed plus omega, etc., 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 etc. Well, they've written it a little bit differently, trying to trick us, I suppose. But we don't get fooled. That's just the standard question, show that 1 plus omega, they just move the 1 to the other side to try and be clever. So all right, z to the power of 9 minus 1 equals 0. I'm going to say, well, I know the sum of the roots is equal to 0. Oh, look, I can move the 1 over. Ta-da! Now comes the fun part. Okay, cos pi on 9 times cos 2 pi on 9 times cos 4 pi on 9 is equal to 1/8. Okay. Well, z to the power of 9 minus 1. I know it'll factorise to be this. Z minus, and each linear factor is z minus the root. But notice I've written it in a very strange order. I haven't gone power 1, power 2, power 3, power 4, power 5. What I'm doing here is grouping the conjugates together. Now, how do you tell which ones are the conjugates? The two powers will add up to be, in this case, 9. So whatever the roots of you're doing, so if it was the cube roots of unity, the conjugate, the two powers, would add up to be 3. In this case, adds up to 9. So that's why I've grouped, I'll go backwards, the 5 and the 4 together, the 6 and the 3 together, 7 and the 2 together, 8 and the 1 together, leaving me with just the one real solution of z minus 1. Now, because these are conjugates, I know the sum of the roots will be twice the real part. And the real part is cos whatever the argument is. So for this first one, well, this was to the power of 1, that was 2 pi on 9. So I know it's going to be 2 times the cos, whoops, wrong one, 2 times the cos, 2 pi on 9. The next grouping would be 4 pi on 9. 2 lots of 2 pi on 9. The next grouping, 6 pi on 9. The next grouping, 8 pi on 9. As for the product of the roots, we're talking about roots of unity. Product of the roots, when you're talking about conjugates, always going to be 1. So, plus 1, plus 1, plus 1, plus 1. Okay. Now we're trying to get that expression. Oh, be real careful with this too. Remember, it's cos, not cis, because we're just writing the real part down. Sometimes people like to write the z after the 2, just so it doesn't look like I'm saying cos of 2 pi z on 9. It doesn't really matter. Okay, but I want to get this middle term multiplied by that one, multiplied by that one, multiplied by that one. So what I'd really like in each of those parentheses is for z squared plus 1 to, well, disappear like it was nothing. Well, how do you make z squared plus 1? How do you turn that into nothing? Oh, what was that one? I heard someone say it. Sub in I. Because then z squared will be negative 1. And then you'll have negative 1 plus 1, and I'll just be left with a single term. So if we sub in, let z equal I. So subbing in, I get I to the power of 9 minus 1 is equal to I minus 1. The i's have disappeared in the first one, leaving me with just minus 2 cos 2 pi on 9 I, minus 2 cos 4 pi on 9 I. Z squared plus z plus 1 just becomes I. And then the last parentheses, minus 2 cos 8 pi on 9 I. All right. So, bit of factorising to do here. I've got common factors here of negative 2i, negative 2i, negative 2i. I can pull those out. The i's have it. Sorry. So I've got I minus 1 there still, but that, just dealing with the i's, I times minus I times minus I gives me minus I to the power of 4. I to the power of 4 is, okay, so I just have minus out the front here. Look what I did on the left-hand side. I to the power of 9 minus 1. So, we now have minus 1, because I've divided both sides by I minus 1 now, equals 8, because now I've pulled out the 2's. 2 times 2 times 2 is 8. Minus 1 is 8 cos 2 pi 9, 4 pi 9, 8 pi 9. But hang on, the question didn't have 8 pi on 9. The question had pi on 9. Well, the cos of 8 pi on 9, 8 pi on 9, choose angle, I'm in the second quadrant, so it'll be negative cos, the acute angle would be the missing bit, which must be the pi on 9, to take it up to a full pi. So minus cos pi on 9. Oh, there's another negative. Divide by the negative, divide by the 8. Voila. We eventually have it. Cos pi on 9, cos 2 pi on 9, cos 4 pi on 9 is 1/8. That was a nice little HSC question there, I thought. Woo! Okay, so let's play with the roots of unity. We've got some Cambridge questions, we got some Patel questions, and hopefully, for me, you'll have questions.